Now let's talk about conditional distributions. Okay, we talked about conditional probability early on in chapter 2, chapter 3-ish. Okay, and then later we learn a lot of different distributions, their properties. So we are ready to talk about conditional distributions, and then in particular in the context of when they're independent. Okay, all right, so recall, so this is from chapter 2 and 3-ish. Recall that for any two events, E and F, okay, the conditional probability of E given F is defined by, as we know, the left-hand side is the conditional probability, right? The right-hand side is the ratio of the joint over the marginal, okay? So provided that the denominator is positive, okay? So this is required. And then what we talked about is that if there are discrete random variables, okay, if X and Y discrete random variables, then the conditional PMF, okay, of X given a particular Y becomes, okay, so the notation as we know before is that we're writing in the subscript, right, X given Y to represent is the conditional distribution, okay? So it is equivalent to, like we are saying, I guess verbally just now in plain English, is that that's the probability of X taking value small x when or given Y is taking value small y, okay? So if we keep doing this, we know that, well, when you're working with a conditional, you can always go back to the ratio, right, of the joint over the marginal. So what we're doing here is that we're getting the joint probability of X equals to X and Y equals to Y, okay, divided by the marginal Y equals to Y, okay? So lastly, mathematically, what you can write is that this is the joint, right, of the PMF, and this is the marginal of Y, okay? And then, of course, we need to make sure that the denominator is positive as well. And just to refresh your memory, how to get this, okay? So if you remember, when we're working with discrete random variable, you're pretty much just trying to sum over the other random variable, right, from the joint PMF, okay? So we did an exercise earlier, I think for part 1 of chapter 6, okay? So this is hopefully still very refreshing your mind, okay? And then, okay, we can, of course, have the conditional CDF, okay? The conditional CDF goes in this way, and then, of course, we use capital F, okay? And then mathematically, what this means is that we're trying to get the probability of X is smaller or equal to small x, given that Y is smaller or equal to small y, okay? And then, of course, in order to do that, right, like, again, this will just be equivalent of integrating, sum over, okay, not integrating, right, because we're working with a discrete random variable. So we're summing over, right, the conditional distribution that we're able to show, conditional PMF from the earlier slide, right? And then only looking at all of the cases when X is smaller than A, where is the A value that we're working with, okay? So lastly, it's important to note, and that's the newest material for what we talked about so far, is that if X is independent of Y, okay, what you can do, okay? So if X is independent of Y, then, well, something very not surprising gonna happen, okay? As you can see from the result, if X is independent of Y, then the conditional PMF, right, becomes, so if I write this, right, becomes the marginal PMF of X, okay? So remember, in the past, we talked about when they're independent from each other, meaning that knowing, like in this case, if X is independent of Y, meaning that knowing Y does not affect our knowledge about X, okay? So not surprising, like I said, the final result is this, okay? But let's now work into the math that we already just learned, okay? So mathematically, right, we're trying to find out about this conditional probability, okay? And then we know it's gonna be this ratio, okay? And the important part, let me just use a different color to highlight, okay, is between this step and this step, okay? So when they're independent, right, immediately we should think about that the joint probability becomes the product of the marginal, okay? So you can break the joint into the product of the two, okay? And as soon as you do that, you can see that, well, we can cancel out the part about Y, so that's why in the end, you only have X left, okay? But also intuitively, hopefully it makes sense to you as well, is that if X is independent of Y, knowing Y does not affect anything about your X, okay? So that's why you will have this result even without doing the math, okay? But I would just highly recommend you to think it through and then feel comfortable about everything we do, okay? Okay, so let's wrap this up with an example. Suppose that 3 balls are chosen without replacement from an urn consisting 5 white and 8 red balls. Suppose the white balls are numbered, okay? And let xi equals to 1 if the ith white ball is selected and 0 otherwise. Calculate the conditional PMF of function x1, given that x2 equals to 1 and the second part is x2 equals to 0. Okay, so if you want, feel free to take a moment before you keep watching. Okay, it will be good for you to attempt it before looking at the solution. All right, so we need to do the conditional PMF. Okay, and conditional PMF, based on what we learned from previous slides, right? You can always get it from the ratio of the joint over the marginal. Okay, and let's see what we can do here. Okay, so eventually we want to get the conditional. So like I said, you should start with the joint and then figure out how to get the marginal and then take the ratio. Okay, so let's start with getting the joint. Okay, the joint is when we write px, okay, px1 and px2, okay? And it's the joint PMF of x1 and x2, okay? So the probability, okay, how to get those probability. So p00, meaning that you're getting x1 equals to 0 and x2 equals to 0, okay? So think about what it means in the context. So xi, right, equals to 1 if the ith white ball is being selected and 0 otherwise, okay? So, and don't forget the white balls are numbered, okay? So we're focusing, right, on the first and the second, I guess, the first 2 white balls in particular, okay? So let's think about the probability, the joint probability of P00 here, okay? That's when x1 equals to 0 and x2 equals to 0. So what does that mean, okay? So remember, we're trying to figure out a probability, okay? And it's a probability, again, we have 13 balls in total. We care about the white balls, and then we are selecting 3 out of the 13. So due to the fact that they're equally likely events, right? So we're able to, first of all, get the denominator, which is 13 choose 3. So remember, you're chosen without replacement, okay? So 3 balls out of 13 balls in total. So it's always 13 choose 3 in the denominator. So that's good, okay? And the second here is that, well, notice that we are having x1 equals to 0 and x2 equals to 0 in this case, right? Meaning that the first and the second, both of the 2 white balls are not selected, okay? So the number of ways to make that happen is that we don't choose any out of the 2, right? That's why you have a 2 choose 0, okay? And the other one is that, well, now we have 11 balls left. So that's 2, like, because we are not choosing the 2 white, right? So 13 minus 2 is 11, okay? And you choose all of the 3 balls out of the 11, which gives you 15 over 26, okay? So similarly, okay, let's look at this one. If x1 equals to 1 and x2 equals to 1 as well, we all, again, start with this denominator of 13 choose 3, so that's good, okay? And then the numerator, because both of them are 1, meaning that both of them are selected, right? So it's a 2 choose 2 up here. Okay, and then of course, with the remaining 11 balls, we only need to choose 1. So that gives you 1 over 26. Okay, lastly, we are figuring out this P01 or P10. That is one of the first 2 white balls are selected, but not the other. Okay, so that gives us 13 choose 3, right? 13 choose 3 again is in the denominator. And then for us, whichever we do, like either one is the same probability, so we put it in one equation. But if we focus on this one, what this is saying that is the first one is not selected, but the second one is selected, right? So we need to select that first, the second one in this case, okay? But then the remaining 2 has to come from the remaining 11 because the first one cannot be selected. So this case, it's 11 choose 2. Okay, and similarly for this case as well. Okay, you're gonna have a 11 choose 2 times 1 choose 1. So in the end, you get 5 over 26. Okay, so hopefully this part makes sense. Again, it goes back to earlier chapters about equally likely events, right? And I would just also highlight that whenever you're working with this type of questions, make sure that all of the probabilities that you calculated, they should add up to 1. Okay, so don't forget this is multiplied by 2 because you have all of them. And this 4 different cases, they exhaust all of the possible combinations of x1 and x2. Okay, so if you do the math, I'm sure it's going to be summing up to 1. So that is a good indicator saying that you have done it correctly. Okay, all right. So that's about the joint. Okay, and we know that in order to get the conditional, right? We're trying to get the conditional of x1 given x2, right? And then whatever value of x1 and x2 over here that we're doing, small x1, small x2, right? We know that we're doing x1 equals to x1. Let me try to write it, okay? Yeah, and then that's the joint, right? Divided by the, in this case, because it's conditional x2, so we're divided by the marginal over here, okay? So in order to get when x2 equals to 1, well, you're replacing, let me just use a different color here, right? You're in part 1, so let's just say in part 1, you're replacing all of this as 1 everywhere, right? So that requires you to figure out the marginal of x2 equals to 1, and then also the joint, right? When x2 equals to 1, and regardless of what x1 equals to. So to get us started, let's look at how we can do part 1 first, okay? So we first of all need to get the marginal probability, right, of marginal probability in this case when x2 equals to 1, okay? So that is equivalent, right, to integrate, or sorry, let me take that word back, to sum over all of the possible values of xy, okay, when x2 equals to 1. Okay, so this goes back to previous part 1 of chapter 2 or chapter 6. Okay, so that means we need to sum up p01 and p11 because both cases you have x2 equals to 1. Okay, so you go back to the calculations that we did, which when you find the sum is 6/26. Okay, so in order to get the conditional, what you do is the first part, right, is to get the conditional of 0, 1. Okay, so that is when you have the joint of 0, 1 over the marginal when x2 equals to 1, which is 5/6. Okay, so again, this comes from this probability that you did. Okay, and then the second part is the conditional probability of 1, 1. Okay, so that's the joint over the marginal, which is 1/6. Okay, so similarly, just like what I was talking about earlier, how to check your work. So for all of the joint, you should make sure that they add up to 1, okay? And also for the marginal, okay? The 2 marginals that you computed, they should add up to 1 as well. So that's another way to check your work, okay? So that's for x2 equals to 1, right? So hopefully part 2 won't be that bad because right now you're dealing with the case where x2 equals to 0. So you start with finding the marginal probability of x equals to 0, which is 20/26. And then you do the 2 separate two separate conditional in this case. Okay, so actually, like for both cases, it's the entire thing is the answer. Okay, and that is because this is a discrete random variables that we're working with. Okay, and then we do have different cases of 0, 1, like 0, 0, 1, 0, and then 0, 1, and 1, 1. So the entire thing is the answer. And you can leave the answer like that once you get to the probability. And lastly, right, like I said, always double check your work. They should add up to 1, okay? Because of the law of total probability, okay? You exhaust all of the possibilities, so they should add up to 1. And similarly up here, they should add up to 1 as well in terms of the joint,